Hi, my name is Will Mulhern, and I will be presenting implementing advanced control algorithms for robotic and autonomous systems. I'm pursuing a Bachelor of Science in Computer Science, and my project director is Dr. Pan Zhao. So we'll be starting off by going over what robotic and autonomous systems are. At a base level, these are machines that perform tasks without human input, so they can do things like make autonomous decisions, operate in dynamic and real-world conditions, and they most often utilize sensors for environment perception as well as for perceiving their internal states. They have a lot of uses. Most often they enhance the efficiency, the safety, or the precision of the tasks that they're used for. We'll now go on to talk about some of the applications of these robotic and autonomous systems. One of the most interesting ones is autonomous vehicles for transportation. We've seen a lot of activity in recent years, for example, with companies like Tesla's that are looking to improve the autonomous driving capabilities. Similarly, they can be used for drones for things like delivery or surveillance. The US government uses autonomous drones for surveillance pretty frequently, and companies like Amazon are experimenting with developing drones for delivery. There's also robots for assembly or manufacturing. Again, in the automotive industry, this is extremely commonplace. Again, for example, with Tesla, they use these to drive the cost down of their cars and also to increase precision. There's also medical robots, which again have increased the precision of surgeries that doctors can do and the repeatability of these surgeries. There's agricultural automation for things like precision farming, and there's also really interesting disaster response and search and rescue robots. The picture at the bottom that I've included is the Spot robot, which you may recognize. An interesting feature of this robot is that it can navigate in very uneven terrain, and it can also navigate in areas where humans can't go. So for example, if you had an irradiated area, it would be useful to use the Spot robot to go ahead and check it out as opposed to people having to go in there. So there's a lot of uses for robotic and autonomous systems that make our lives easier. So moving on to what control algorithms are, these are the algorithms that govern the behavior of the robotic and autonomous systems. The most important thing to know about these is that they utilize real-time feedback for adjustments. As I mentioned previously, they sense their external and internal environments in order to make these decisions, and they govern the system behavior under a certain variety of constraints depending on the purpose of the robot. They also excel at adapting to changes and uncertainty. So as I mentioned with the Spot robot earlier, for example, it can handle uneven terrain, which is not something that many human-led robots can do, and not something that other machines can do as well. So next, we're going to talk about the UA Autonomous Systems and Control Lab. So here are a couple of the projects that the lab has been working on over the past years. Now, some of the overall objectives of the lab are implementing advanced control algorithms as a whole, and then testing these algorithms on things like a 2-degree of freedom platform, which I'll get into later, and then also using the OptiTrack system, which you can see on the photo on the left. That is a 3D imaging system which can track a drone anywhere within that cage. And then finally, the lab has the goal of validating these advanced control algorithms under a variety of conditions. Since we're focusing on drones, we would focus on things like different payloads for the drone, and also an interesting category, which is propeller damage. So how can you maintain stability of the drone if the propeller is damaged, especially in a varying environment? So for my specific project, the goals were to develop a linear quadratic regulator for the 2-degree of freedom drone platform. I'll get into what that is later. I then wanted to simulate that in MATLAB/Simulink, and then finally to experimentally validate that model on the drone platform. So first, we'll get into what a linear quadratic regulator is. It is one of the most commonly used controllers in many industries like robotics, aerospace, and the automotive industry. It optimizes the system performance using control inputs and helps to balance that performance using state feedback. To put this in layman terms, the LQR basically seeks to stabilize a system around a desired point, around a desired control output. Next, we're going to talk about what the 2DOF drone platform is, the 2 degree of freedom platform. So here we have a close-up of the actual setup we have at the lab, and I've overlaid a little drone to help exemplify this. So the 1 degree of freedom that we have is horizontally. As you can see, the drone can slide along those rails. And then the other degree of freedom that we have is actually a rotational degree of freedom. So as you can see, it can roll along that axis. But importantly, it doesn't have the other degrees of freedom, meaning it can't move forward and backward, and it can't move up and down. So next, I moved on to designing the LQR controller in MATLAB. This includes a little linear algebra, some state matrices, and parameters matrix for tuning the LQR, as well as the computation of the LQR gain. Again, this, in layman's terms, basically is just the base settings that allow this algorithm to stabilize the drone. Here is the Simulink model, and I want to draw your attention to the block on the far left. That's the stepper block, which allows us to sort of test the overall model of the system. And in the middle, you can see the overall model of the system. And then finally, we move on to our simulation results. So the yellow is that stepper that I drew your attention to previously, which basically outputs our desired control output. And then the other 4 values are our state values that, as you can see, stabilize. So we have the position values stabilize around that stepper output, and then the velocity outputs stabilize around 0. So our future directions for this research are testing it on the 2 degree of freedom drone platform. We had some delays in getting the software needed to put it onto the drone. Another future direction is designing and testing machine learning-based control algorithms and implementation and testing of these algorithms on 3D drones, as well as testing the algorithms under varying conditions like different payloads and propeller damage. Thank you. Are there any questions?
Thank you for your presentation. I was just wondering, could you provide a real-world use of an LQR?
Yeah, so as I mentioned previously, LQRs are most commonly used in the aerospace industry. So they're used to stabilize things like planes, helicopters, and in our case, drones. But they're also used in a variety of other industries. One common one that you might use every day is in the automotive industry, cruise control. But it's used basically everywhere that there are robotics. Thank you.
Why did you choose a 2 degree of freedom platform?
We chose a 2 degree of freedom platform because it's easier to experimentally validate the algorithm, and it also better isolates the variables. So we can expand the algorithm to work on 3 degrees of freedom once we've experimentally validated it on the 2 degree of freedom platform. And this is more important for something like a machine learning algorithm as well. Thank you.
In a real-time system, a correct answer delivered late is a wrong answer. So you use an example of cruise control. You know, if the cruise control doesn't respond quick enough, you're going to rear end the car in front of you. So how could you add like real-time kind of concerns into the testing environment that you're looking to build?
Yeah, so that's what that Simulink model is for. So I can actually go back to that here. So you can see that the current state actually loops back into the control algorithm itself. So that's what most of the current things like linear quadratic regulators are built around, is consistent, like constant feedback back into the system, because it sort of iteratively provides the best like amortized output. And that happens like really, really frequently. So it's not like once every second it will do that. It'll do that hundreds of times a second and make a lot of micro adjustments. Thank you.
Would a machine learning-based controller perform better?
There's a potential that it would perform better. Linear quadratic regulators are limited in the fact that they are not the best at adapting to really unforeseen changes. So something that I mentioned earlier in my presentation was the fact that in real-world environments, there are a lot of unpredictable forces, things like wind or uneven payloads or your actual machinery breaking, so something like a propeller breaking on the drone. So machine learning algorithms have the potential to be much better at adapting to those type of changes than a more hard-coded algorithm like an LQR. Thank you. Thank you for attending RRS Live Day 1, and we hope to see you tomorrow.